Hi, folks. Welcome to Drake's Lounge Australia for September 2024. It's the 28th of September in Australia, 27th in the US. Welcome to everybody. I'm Andrew Claycotrick, standing in for Paul Butler, who's away this session. I acknowledge and pass respects to the traditional and original owners of the land on which we are meeting today. And as is traditional, we'll start off at the Australian end and then pass over to the US for a catch up on what folks have been doing in radio astronomy for the last month or so. And I'll go around the room for the Australian side. And next on my list there is Steve, who's in Melbourne or Sydney today.
I'm a Melbourne person, Andrew.
That's right. Great. All over to you.
All right. Good morning, folks. Nice to be on the session once again. I don't have a lot to present in terms of discoveries or surveys or measurements, observations, whatever, but I can give an update, a brief update on the progress of our 8.5 metre tracking dish up at Heathcote. And I'll bring just up a few slides to have a look at. So you may recall we had that worn out worm drive that does the altitude adjustment, the jacking adjustment. So that was all now ready to go and reinstall it. So the first thing that I didn't participate. These are photographs taken by our section director, Phil Costigan, and he was ably assisted by Mitch Raitt, who did a lot of the assembly work and fabricating of special fittings and attachments to lift up the items to the tower. It's quite an OH&S nightmare with very heavy items. Had to be lifted several meters above ground. We've got a scaffold to help and block and tackle and things like that. This is the big jacking screw, the 50 millimeter, actually it's bigger than that, 60 millimeter diameter, very hardened steel thread, about nearly 4 meters long. And we lifted that first of all and fitted that to the tower. Let's see the next image. And there it is, fitted to the tilt plate on the top of the tower. This plate holds the actual dish itself. And it's the jack screw is fitted into a plumber block, which rotates, because obviously as the tower tilts, the jack screw has to rotate. And this fitting at the top there, this plate, this disc, is where the bellows that we also need to fit to this system so we don't get dust and rubbish getting onto these threads. This is where some of the wear occurred in the first place. So we had to fabricate these custom fittings to cover up the jack screw. So that's seen in that image there, an item fabricated by Mitch. And block and tackle was used to lift the jack screw. That itself weighs about 50 to 60 kilos. The jack screw takes 3 people to carry it, and you can't carry it for very long before your arms start to stretch. So it's quite a heavy item in itself. So once the jack screw was in position, then this thing here, the big swivel plate, this white thing, is the next part to be lifted. That contains the worm drive that the jack screw goes through, and there's a motor on the other end of that. So that's the whole system that jacks the dish up and down. This weighs about a ton. So that's not a small thing to carry around. Little localized lift systems were devised by Mitch and a trolley to move it into position. And it's seen there, the tower is on the right-hand side there, this white thing on the right. There's our scaffold on the left with the stairs. And you can see they've lined up the swivel plate with its worm drive just below the jack screw. And it was lifted into position. And then the next image shows how we lifted the swivel plate. A electric hand drill was attached to the other side of the worm drive, because on the right-hand side there is an electric motor that actually does the driving, but there's another extension of the shaft on the other side of the housing of the worm drive. And so we made a fitting to attach to an electric drill. And believe it or not, you just wind the drill onto the jack screw and it slowly lifts the entire weight of that swivel plate. It took a couple of goes. It took 2 weekends. They were running out of batteries on the hand drill to lift it up. It also got quite warm, but it didn't damage the drill. And then finally, there it is. The swivel plate is now attached to the fixed plate at the top of the tower. And you can see the fixing bolts there done up. And the top bellows wasn't fitted at that stage, so they just covered it up with plastic to protect it from the weather. But they were able to fit the bottom bellows. And the next image shows that being fitted below the worm drive gearbox. And there's the motor on the worm drive. So the bottom bellows is fitted, and there's an image of it. It looks like there's a bit of bunching in the bellows when it's fully extended like that. That's not an issue, by the way, not a real problem. So the next step, which was progressed during the month of August, and then a bit more in September, was to fit the top bellows. And that was finally fitted only a couple of weeks ago. And when the tower is pointing at zenith, the bellows are fully compressed. And that was one of our main concerns, whether we could achieve that with the dimensions of the bellows we had. It's a very tight squeeze. It gets down to 183 millimeters in that gap. We had to cut lengths off the original bellows as supplied to us so that it would do that crushing down to that size, but it managed to work. This fitting that was attached, that's new. This now gives us the ability to inject grease into the worm gear itself and do some regular maintenance on it. So there it is. At long last, we've now got protective bellows over the jack screw and a means to maintain a nice lubricated joint through the worm drive. So it's ready. It's ready mechanically. There was some rehoming to be done on the motor system to re-establish the travel movements, because there's also switches to avoid driving the system over its range. So Phil did all of that recalibration process on the motor system, and that's fine. So the next stage of activity, which will begin probably starting this month, sometime this month, next month, October, is to work on the cabinet and install the new receiving system. I'll give a brief overview of what's required there. I've got a couple of images that'll help with that. So inside the cabinet, and there's an image of the inside of that cabinet down the bottom there. That's where we're going to fit the receiver. And I've talked about this before and presented some reports on it. So we've got our low noise amplifier will be inside the cabinet, keep it out of the weather. There's the RF switch that goes between the noise source reference and the antenna. So we can do some calibrations against the noise source. A status monitor that looks at all the electronics. We've got several fans in there now for Peltier cell cooling, so we're monitoring everything. The front end box will go down in the bottom of this part of the cabinet, and a main power supply. So I've sort of planned all of this out. None of it's been done yet. We've got to make some mounting brackets to fit some of these items in there. I've just put this drawing up, which is a set of photographs of the actual items themselves. So that's the front end with the Peltier cell cooling and the noise switch in there, status monitor box. And the front end is Peltier cell cooled. Lots of cabling that goes in between this. It looks like a bowl of spaghetti once it's all connected up, but it has been connected up on the bench, and it all tests and works. That was done a year ago now, so I've been waiting a year to get it all wired in. So that's the next stage, connect it all up, get it running, and then we can start doing our surveys of neutral hydrogen and other studies that the Parkes Radio Telescope people in New South Wales are still keen for us to collaborate with them. So we're keen on doing that ourselves as well. Good. Thanks, Andrew.
Yeah, thanks, Steve. That's great to see. It's a really impressive setup there, and yeah, heavy machinery. It's always tricky to deal with, but it looks like you've got a great bunch of people working with you there. Wendy's posted a question in the chat. Where does one purchase the bellows? Of what materials are they made? And great presentation, by the way, from Wendy.
Oh, thank you. Look, I'll have to get back to you on that. We purchased them from a firm in New South Wales. I could look that up. I'll do that while we're doing a rounds with the other people. They're made out of material that's like swimming pool plastic. It's very tough, very resilient, and very waterproof, very waterproof. There's also inserts inside it, nylon sleeves and nylon discs that sort of segmented every 11 leaves. You've got one of these little inserts in it, and that just helps it sort of spread out rather than bunching up. And those inserts were critical, but with the top bellows where it compresses right down, we actually had to remove one of those inserts, one of the sleeves, and that's where it got shortened up. But it's stretching from 180 mil on the top when it's compressed all the way out to nearly 2.9 meters. So it's quite a dynamic range, and it works. It seems to work. But in the operation of the dish, we don't normally put the dish at zenith. In fact, that's a point that's very, very hard to sort of do anything with. You know, if you want to track something over the zenith, you sort of get to a point, then you swing the dish around, and then you come back again. So that's a point that we can actually avoid in the software of the dish operation, and also pointing the dish at the horizon where you fully compress the bellows. That's not a normal mode of operation either, because you're picking up ground noise. So you're normally about 20 degrees above the horizon, but we will need to go down to that point for maintenance on the cabinet. So it's still something we've got to consider, but it appears to be okay, fully compressed. All right, stand by. I'll get that information for you.
Yeah, thanks, Steve. That's great. Yeah, great to see
Thank you,
some.
Steve.
Yep. No, Wendy. Yep.
Oh, I just wanted to say thank you. My computer setup is kind of dodgy as far as microphones and stuff is going on. So I thought I'd say thank you in person while I can.
Great. Thank you. Any further questions for Steve?
Yeah, I have a question. How many turns of the drill does it take to move that thing 1 degree?
Oh,
Or the motor when you get the motor there? What's the ratio?
well, the motor itself, the motor is in a gearbox. There's a motor driving a motor gearbox. Then the motor goes into the worm drive. So there's a number of down ratios.
Oh, okay.
And the motor itself is a stepper motor, a 3-phase stepper motor, and it's millions to one. Like, it's pulse controlled, and the gearing is extremely fine. I don't actually have numbers off the top of my head, Bob, but it's never been an issue with the requirements for getting within a fraction of a degree of the telescope position.
Okay, great.
But the hand driving with the electric motor, that's a little bit more coarse. In fact, I was surprised the guys managed to do that, because they were also back driving the motor and gearbox, which was also attached to the same shaft. But it didn't seem to be a problem. The motor and the drive was freewheeling as they were cranking the thing up. It was a novel way to do it, but it was also the safest way we could lift that heavy mass and also have it all connected to the jack screw. It's very precarious, that process. Should have seen us when we tried to lift it down, and I won't go into that. That was a risky job.
And do you have a brake on it also?
Yes, there are brakes, and there's also the motor control system has got ramp up and ramp down in the software program.
Okay.
And in the braking system, there's ballast loads inside the electrical cabinet that runs the thing. So these ballast loads get hot when you do the back EMF side of the braking.
Ted's got a question there. Did the dish have bellows recently before you started?
Oh, no. No, this is it. We put the dish up just before the pandemic, and we got it to work. And I was using it. We can remotely control the dish from home, and I had it with interface to the receiver output, collecting data from the receiver, controlling the dish. It was all wonderful stuff. It's fantastic the way we've got it working. And I used it for months, and I was driving the thing around, collecting data, and I actually prepared a couple of reports for the society on the results I obtained. However, unbeknownst to me, we were slowly but surely wearing out that jack screw. And when the pandemic came off and we were able to get up there a few times, we did a few more exercises while we were on site. And then we noticed in the process that as we took the dish through the tipping point, there's a sort of a balance point where the mass on the jack screw goes from one side to the other, and the dish went boing like that. And we thought, oh, that doesn't look good. So that was when we pulled the thing apart and found the worm drive itself, the phosphor bronze worm drive was worn out to the point where it was about to break. And I think I've explained in the past there were two reasons why that wear was occurring. One is that we didn't protect the jack screw. So dust and rain and whatever is getting into the thread of the worm drive. So that's one thing. But when we examined the jack screw itself in great detail, we found there were spots of weld along the thread, because this had been a second-hand jack screw. It wasn't brand new. It was probably lying in a factory somewhere where it came from, maybe next to a welding machine. It had spots of weld on it, and it was so embedded into the thread, it prevented the new worm gear we purchased. We couldn't get the worm gear past these little welds of spots of weld on the thread. So it wasn't possible to remove those little specks in there by a file. They had to use diamond abrasive tools to remove these little spots. And then when that was done on about 6 places along the thread, this is horrendous if you think about it, then the new worm gear was able to go right through the whole thread without any stixture. And that tells me that was probably the primary cause of wear in the first place, not so much dust and ingress. But we should now theoretically get a much longer life out of this operating system by maintaining it, keeping it clean. And we've got a spare insert of that worm drive thread as well. So when things do need to be serviced, we've got another one to go to. But I'm hoping we don't see this problem for many years to come. One of our team members, Tim Davis, Dr. Tim Davis, he's spent some time in Germany over August and September. He's back now. He's going to be a protagonist in our surveys. He's going to help write the software that controls the dish, collects the data automatically, so we can set up some survey routines, and then we get the data, and then it's a case of post-processing data, as you know. So I'm very keen to have Tim back on the team, and he's keen to get stuck into it as well. So with a bit of luck, fellas, we'll get some results before Christmas.
Yeah, brilliant. So that's great. And Preston says excellent work too in the chat, of course. So we're looking forward
Now
to
the dish, it has azimuth control as well?
Yes, it's an alt-azimuth system, so we can rotate the dish and we can tilt it. Yep.
Very good. And so then you'll spin it around to the tower and work on the feed and stuff. Yeah. Okay,
Yep.
thanks. I just haven't seen that move yet too. I'm eager.
Oh, we should present a video at some stage. I'll make sure we get some up-to-date information about how it works. I haven't been up to Heathcote for a while, but with our winter, I was involved in some skiing activities in our snow mountains.
over to Len, who's in Melbourne.
Oh, hi everyone. I haven't got a lot to update. Just a reminder, I've got a 2.4 meter dish in my backyard that I've been doing hydrogen line work on. But I also previously, about 30 years ago, I worked on a 3 meter dish on top of the Redmond Barry building at University of Melbourne. We converted an old weather array into a little radio telescope and LEO satellite tracking system. But it for the past 20 years or so, it's been in disrepair. So some students wanted to resurrect it. So I've been asked to sort of help. I did the software, the drive system and encoders for that 30 years ago. Funnily enough, I've still got the code. Yeah, so we'll have a go at resurrecting that. Probably also just to do hydrogen line work because it's a mesh dish. So that's so I don't have a lot. I've had a lot of work getting in the way of the hobby. So yeah, so that's it. Just don't know how to get.
Glenn,
Yes.
the small dish that you're showing on your those have been available now here in the States as a so-called solar cooker.
Okay.
That's what it is. It's I can
Yeah.
recognize from the hexagonal opening at the base.
Yeah.
And they're available here now for about $75.
Yeah.
It's just it's an incredible
300. It was
buy.
yeah. Oh, I mean, it weighs a lot. It's 80 kilos. But it's a C-band, and I thought, well, maybe I might want to go higher frequencies later. So,
It'll
yeah,
work.
but it's
I'm going to try one at 10 gigahertz.
yeah.
I think it'll work just fine, but I want to do a Cassegrain feed, which I think is
Yes.
what you're showing there.
Oh no, this was
No?
construction. I've got just a feed,
Can feed.
just
Yeah.
a can. Although it was I also had a choke, but the choke was too complicated to mount, so I've just gone simple for the moment, and it works. I've shown
Right.
previously the results, but yeah, it needs a bit more work.
It's I think as long as these things last on our available, I mean, I got it on Amazon for heaven's sake. Took something for somebody to cook beans with, but it's a nice piece of steel, and comes well packed, and man, I think it's a great buy. I'm trying to promote it for people here.
I did have to change the struts that go up to the feed horn because they were circular and they were flimsy and they were bouncing all over the place. So I went down to the hardware store and bought some square aluminium, square steel, and now that the feed's not moving.
Oh, that's good. They have some strange kind of thing that pokes up through the hole and is fixed vertically. I don't understand how they hope to cook beans with it, except except over a very limited range of azimuth or elevation angles. But but it comes with a little hand crank arrangement. I haven't yet put it together. Somebody in England has gotten it and is working with one. And has put the measurements on the Sarah list. It's a 0.31 F to D, and it's pretty obvious what they did because the diameter of it's 1,500 1.5 meters.
Yeah.
And
I see. Yeah, mine's 2.4 meter, but it's, as I said, a C-band dish that weighs 80 kilos. So it's actually
that's a little bigger than the okay.
Yeah.
But it looks like the same manufacturer. That's interesting. Because of that hexagonal.
It's probably just the way the petals come together.
Yeah.
Yeah, that was before I had the cover on it. So there's a cover that goes over that. But yeah, Cassegrain is a possibility, but I'm just keeping it simple at the moment.
Right. Okay, thank you. Sorry, I
No worries.
Went off, but it's such a heck of a deal. I can't believe it.
What I'm afraid of is if we all buy one, the price will go up.
Well, hurry. No, what I think will happen is they'll run out of them because I think this is some kind of a warehouse buy that somebody's made, and they've adapted a few of these to solar. Somebody said, "Oh, let's make solar cookers." Okay, but when they run out of them, there won't be any more. And so that's what I'm thinking. I don't think the price will go up.
Well, that's a thought. I mean, that's another good reason. Either way.
Yeah, yeah, it's
Yeah, thanks, Len. That's great. Yeah, it's interesting. I hadn't come across those solar cookers. I must have a look myself, see what they're all about. But yeah, trying to get a low cost big dish is yeah, it's interesting. They are around, but I have seen plenty of surplus ones from a lot of the TV stations that used to have big dishes that now got smaller ones. But yeah, they're very useful. Yeah, thanks, Lynn. That'd be great to see that Leo dish going too, doing something. So look forward to hearing about that one. Now we've lost Duncan. He's probably rebooting. So we might go over to Roger if Roger's there. And go, Roger.
Hi, everybody. Really nothing for me to report again. I keep saying I'm busy, and I probably will be till Christmas time. Interesting to see a couple of things on the last couple of ones, and then Steve's dish. I remember those. Was that the ones that came from the CSIRO? Yeah, we actually looked at getting one here. It looked very similar to that too.
Our 8.5 meter dish, Roger. That's
yeah, the big
ex-Telstra.
one. Yeah.
That's ex-Telstra.
Oh, okay. There you go.
Or Telecom Australia would have been. They used them to do propagation studies between mainland Australia and Tasmania, across Bass Strait. They did a number of tests at different locations, different heights. Then they became superfluous, and a lot of radio amateurs bought them. And we actually purchased ours from a radio amateur who never got around to using it.
Okay, very similar to one that we saw from the CSIRO. I mean, I know Telecom. I used to work for them, and I almost actually got a job in their research laboratories, which were in Melbourne. But that was 40 years ago. Now it wouldn't have been around at that time, but it would have been good to have been there. And also noticed Len's. I was looking at his dish. I've got a 2.4 meter dish to work on, and the way that you've actually set up your feed there is what I was considering doing. I've bought myself some struts to basically put the triangular section much further out than the feed horn, just so I can get some adjustment, have a bit of a play with different feeds. So that's all good. But at the moment, yeah, just a bit busy. I'm hoping by Christmas time I might get around to doing a bit more. Haven't really done much in the society here in that time for the same reasons, but we will get back to it. So, yeah, not much more to report, and I'll just keep listening in. See ya.
Cool. Thanks, Roger. Yeah, hope things go well for you and get back into the astronomy there, and look forward to seeing some things from you next time. Now Duncan's still offline, so are there any other Australian folks in the area? I don't think we have any other Australians at the moment, aside from myself. And I might just try and share my screen. I've got a few results. I've been getting close to getting back into some hardware, but in the meantime, I've been having a bit of a look at some of the data I've collected over the last couple of years with low frequency radio spectrographs. So mainly the sun, but also Jupiter. And I'm kind of interested in using solar type 3 radio bursts to give me a bit of an idea of how low in frequency I can observe, and whether it be galactic or even Jupiter radio noise. So solar type 3 bursts are pretty useful because they are plasma emission that occurs to very, very low frequencies, down to kilohertz. And I'll show you in a second some satellite measurements that confirm that. So they're kind of a probe for how low in frequency you can actually observe. And of course, one of the limiting factors is the ionosphere. And I show you this paper here, which I think I've shown earlier in the year. This is an open access paper in the Journal of Atmospheric and Solar Terrestrial Physics by some folks from the Ukraine, which have used type 3 radio bursts to look at the ionospheric critical frequency. And so normally during the daytime, you can expect to see galactic or any other extraterrestrial solar emission down to a frequency which is limited by what's called the FOF2 ionospheric critical frequency, which is the frequency measured by ionosondes. So these are radars essentially that send a signal up to the ionosphere, and if it passes through, or at the frequency it just starts to pass through, that's called the vertical incidence critical frequency. And if you're looking at a source that's off the zenith, normally the lowest frequency you can observe to is given by this formula here. So we've got the ionospheric critical frequency, which you can get from an ionosonde, and alpha is the solar elevation angle. So normally this frequency is higher than the critical frequency that you observe from vertical incidence. Anyhow, so I've been using some solar type 3 bursts. So these are measurements I've made with my small radio spectrograph. This is akin to, I guess, the type of measurements that the Radio Jove people make. So I've got a loop antenna with a preamplifier and a small SDR. It's a RSP1 spectrometer, and I'm using radio sky spectrograph to record this continuously. So I make these measurements 24 hours a day. Generally, the antenna's pointed north-south. I can move that around. In fact, I'm looking at putting a second system in so I can actually do some direction finding on the measurements. But here's a group of solar radio bursts, and you can see that the lower frequency is moving down. This is going from about 16 megahertz to 24 over about 45 minutes back in April last year. And the sun's actually quite close to the horizon, so it's really only a few degrees above the horizon. As the sun's rising, the lower frequency that I'm seeing these bursts to is actually going down in frequency. So I've been having a look at, does this equation give me an accurate measure of the lowest frequency that I'm seeing these bursts to? And the answer is no at the lowest elevations, and there's some interesting propagation happening there. And in fact, I'm seeing radio bursts to frequencies much lower than I would actually expect to see at these low solar elevation angles. And the handy thing about this is that when I'm looking for Jupiter's often fairly low in our sky at the moment for the southern hemisphere. It's quite good for the northern hemisphere. But if I was doing a simple calculation as to what the lowest frequency I might see Jupiter bursts to, I actually find I can actually see them to lower frequencies than I would expect from this equation when Jupiter's low in the sky. Now these radio bursts, then I'm not limited by my sensitivity or the lowest emission frequency of the radio emission. So these are measurements from the wind satellite, which is at the L1 point between the Earth and the Sun, and it has a low frequency spectrometer on it. You can go to the site here and have a look at this data. So here are the radio bursts here, and they're going down. The upper frequency here is 16 megahertz, going down in this case here to a couple of megahertz or even lower, maybe 1 megahertz. So it's not the fact that the radio bursts end at some frequency here, it's just really the ionosphere that's limiting me. And it's not the sensitivity of my radio telescope that's limiting me. So I've gone through and looked at all of these type 3 bursts over the last year or so, checked to see if they're really type 3 and seem to low frequencies, and then got the ionospheric critical frequency from my local ionoson, which is literally only a few kilometers away, and then had a look at the validity of this equation here. So here's some results. And what I'm plotting here, there's a number of type 3 bursts I've observed at different solar elevation angles. And I'm showing the difference observed minus calculated frequency from that equation. And what this is showing essentially is if the equation was a perfect representation, I'd expect to see a cluster of points around the 0 difference here. And generally I've got a bias. So I'm actually seeing bursts to much lower frequencies than I would expect the equation to tell me. And this is a bit counter to the paper that I showed, where they actually showed some really nice examples from a big telescope in the Ukraine, where they showed almost a perfect match. And well, yes, there are a few occasions when the equation is quite a good representation, but generally there's a bias here. And sometimes, in fact, I'm seeing bursts to higher frequencies than I would expect. So I'm really sort of scratching my head a bit here, and I'll go through and have a bit of a closer look at the ionospheric conditions. But it's just a little bit of an example of what an amateur could do. And I'd encourage other people to have a look at this if they've got some measurements of solar radio bursts.
Andrew, is this just a lack of samples, perhaps?
Yeah, so it's only a small sample at the moment, so I'll go back through my results and get some more. But I think certainly at the low end here, these low solar elevation angles, there's some ducting happening in the ionosphere. Maybe it's due to the E layer that sometimes is present.
Yep.
The Ukrainian folks are looking at sort of fairly high solar elevation angles in their paper. And some of these points here might actually be a bit limited by my sensitivity at the higher end. Some of these points are actually at relatively high frequencies, around 30 megahertz, where my sensitivity drops off a bit.
Can I ask you a question about your previous slide?
Yeah, sure.
So what you're doing is your ionoson is producing a transmission at a certain frequency, which I guess is F0 here. Is that right? And then you're measuring F2, which is
it's sweeping through from about 1.5 megahertz to about 30 megahertz. And at the frequency that there's no reflection, that's this FOF2 critical frequency, the vertical incidence.
And do you have any way to sync with them in terms of how they're timing? Is it a slow rate that they're doing this over, or is it fast?
Yeah, it's over a few minutes of scanning through, and I'm picking the value at the time that the ionoson transmits. So this is every 5 minutes in this case, so it's a fairly close matching time. And as I'll show in a second, there are a couple of other confounding factors that alter the accuracy of this equation. But basically, the critical frequency that is being measured by the ionoson should be a good representation of this vertical incidence critical frequency for the use in this equation.
So it's an index of refraction of the ionosphere of that area, that layer, I guess. And then it's changing due to the sun. And
that's right.
You're measuring the critical angle of that refraction, I guess.
Yeah, I'm effectively going backwards and working at what I think the vertical incidence critical frequency is based on these solar bursts. That's another way of looking at it.
Okay.
I have a question, Andrew.
Yeah, go.
In that top right chart, the blue chart there, why is it less sensitive, less information around 21 megahertz?
There are some transmitting stations. So this is like commercial band. There are some amateur bands in here. There are less stations in here. I'm slightly less sensitive in here. You can kind of get a feeling that there's not a big drop in sensitivity because these bursts don't look strongly suppressed in this region. But yeah, there are less transmitters, and of course,
That's an advantage, by the way, because that's the
it is.
Jove.
It is an advantage.
frequency.
That's right. It also depends on where they are. So some are in Australia, some are overseas, and it depends on the propagation conditions
Yeah, of
across the
course.
path for what you get. I guess another thing you can see here that the bottom frequency of these bursts is fairly well defined, but you know there is some ambiguity in here by maybe a few hundred kilohertz. It's not a big uncertainty though. So in other words, yeah, I can measure probably at least to 100 kilohertz as to the cutoff here, and there's quite a strong cutoff generally at the bottom frequency of these bursts. You don't see them popping through again. They all tend to, you know, finish at some low frequency.
It's interesting that that bottom chart very much looks like Whistler patterns too.
Yeah, they are yeah, they're very much dispersed. So these this is plasma emission occurring along open field lines or quasi-open field lines where electron beams are propagating well out into space, and in fact many solar radii, and in fact many tens of solar radii in some cases for these very low frequencies.
Can I make one more comment about it? I'm participating in a group called HAMSI, and I have a station here doing reception of WWV, the time transmission at 10 megahertz, looking for the same kind of a characteristic. And there's a fellow at University of Texas, Dallas, that some of us got to visit with during the recent colloquium, or not a colloquium, but a conference that we had there. And he's doing measurements utilizing the GPS satellites as a transmitter, and he's got receivers on the ground in multiple places, looking at the influence of the ionosphere on its reception there. And so it kind of correlates with kind of stuff you're doing. It looks like the ionoson that you're working with is only varying from like 21 megahertz to 21 and a half, I guess. Is that right?
So the ionoson, the ionoson sweeping over about 1.5 to 30 megahertz. So it should.
Okay, the full 1.5 to 30, and you're just showing us this little snippet that you're working.
It should get a fairly accurate measure of this FOF2 value.
You often hear that on the Jove receiver that we have running at Heathcote. You hear these.
Yes. Now they're more likely to be, the ionosons or over horizon radars.
You hear all of those things. They're horrible.
That's right. Yeah, I can show you some nice images here of all of the Australian.
The HF spectrum is never clean, is it, Andrew?
No, definitely not.
No.
And this is a nice day where it's actually quite
You're
calm.
lucky, yeah.
Yeah.
Here we can also see sea surface measurers.
Yes.
They use a chirp system to measure the sea surface roughness.
That's right. Yes, we have those around Australia. In fact, we have one fairly close to me, and that's quite interesting. Looking at the scatter, the patterns coming back from that. That's something I have looked at. But yeah, back to that GPS. Yeah, I've actually used. So there are some GPS stations fairly local to me, and the Australian network is quite broad, and I think in the US very similar. And you can actually download. I should show an example of that maybe another time, but you can actually download files, and there's a neat bit of free analysis software that enables you to get a total electron content profile for your location. And that's something that I will use with this to get a bit of an idea of the ray tracing. Well, I'll do some ray tracing to try and understand this propagation and this bias here. So yeah, quite useful. And the other thing I just mentioned a little while ago is there are some other confounding factors. So the ionosphere is a refracting medium. So as the sun goes lower in the sky, its apparent position is different to its actual position. Much the same as you see visually. You know, the sun can actually be below your horizon geometrically, but refraction lifts it up. So there's some small angles that affect that alpha value in that equation. And then, of course, as the type 3 emission is moving away from the sun, it can be a couple or several solar radii away. So that varies alpha by, you know, a degree or a couple of degrees. But these biases are much larger than I'd expect from those small effects on the angle of the sun. And by the way, you can get these FOF2 values from this Global Ionospheric Radio Observatory site, which is quite handy. Just moving on, what I've done here is I've plotted the critical frequency that I'd expect from that equation for every 5 minutes of the day from January this year up till recently, when the solar elevation is greater than 10 degrees. And so this gives you some idea of the minimum frequency you might see at least solar radio bursts to. And of course, a similar thing would happen for Jupiter if Jupiter was above the horizon during the daytime. And so I'm going back to have a look at the situation for Jupiter at the times when Jupiter's above the horizon, and also you'd expect to see radio bursts from one of the sources of Jupiter. So that's kind of a thing to help me check my recordings, because I guess one thing that you know, you collect a lot of data and you need some automated way of going back through. And certainly you can use an ephemeris of Jupiter and its expected radio emissions. But you also kind of need to know what the limiting frequency from the ionosphere is. So once I understand this bias a bit more, I might actually get an improved equation, tell me the lowest frequency I'd expect to see radio bursts to, and then I'll combine that with the Jupiter information. And speaking of Jupiter bursts, I have actually made some measurements of radio emission from Jupiter with my loop system. But then I came across this interesting paper recently. This is another open access paper. This is actually in Nature Communications. You can look this one up. And while IO is quite an important instigator of radio emission from Jupiter, there's some evidence now that Ganymede and Jupiter's aurora also produce radio bursts. So this paper has an interesting plot in here. Those familiar with Jupiter radio emission will recognize this. This is the probability of seeing radio emission from Jupiter as a function of the phase of Io in its orbit and the central meridian longitude of Jupiter's system. And there are these preferred regions, these white regions here, A, B, and C. But now this paper also talks about these extra emissions, these green ones and the pink ones. So the green ones are from, it seems, Ganymede, and it might be Ganymede being in particular locations, influencing the IO emission, or interestingly, they've looked to see if Europa is a source, but it doesn't seem to be. You might expect the geysers from Europa to be an interesting source, but certainly Ganymede. Maybe that's an indication that there's some effect of Ganymede's environment on the emission, and then emissions related to the aurora on Jupiter. So I've been going back through to see if I've made any measurements at these particular times here, and I haven't found it yet. But this particular example over here is right in the middle of this IOB source. So you never know. It'd just be interesting to see if there were some more cases, because this is the first paper that really discusses this. And again, it's another activity that amateurs could actually contribute to by trying to understand these emissions as well.
Andrew, that chart on the right, is that a prediction chart or a measurement?
Yeah, it's a prediction. So it's
Okay.
it's a chart from a paper that was produced a few years ago to bring together a lot of observations of Jupiter radial emission over years.
But they
to
haven't
show
included those two new ones you mentioned.
No, that's right. Yeah. So it's a little bit hard to tell from this plot here, but there aren't any really strong sources under this sort of low probability. This is the probability of seeing radio emission. And I should say, it is quite frustrating looking at Jupiter. You might expect to see, in here the probabilities are up near 70%. And in fact, I did see something on this particular day, but you've got to have the ionosphere cooperating. You've got to have Jupiter high enough. You've got to have, no low interference, particularly from the sun. So yeah, it's sometimes hard to see these things. Can be quite frustrating, and they can be quite fleeting. These things are,
and they're also quite weak. Looking at the chart, at your measurement there on the left, they're very faint, aren't they?
They're faint. That's right. So these are only, I haven't got a scale here in brightness temperature, but they equate to not many dB, maybe 5 or 10 dB if you're lucky, and quite brief as well. And so I think you were saying you're monitoring at a single frequency.
Yeah, I think it's the NASA Inspire project, and I think that's not really suitable anymore. I think your method of a wider spectrum and software and a waterfall type display is a better way to go.
Yeah, certainly you can pick out, this interesting structure which looks different to anything else. It's quite different to radio interference, for example. So
yeah.
But anyway, yeah, a couple of things there. Hopefully, if you've got some data on the sun and Jupiter, you can go and do a bit of.
Can you put that on the chat window, that little presentation, please, Andrew?
Yeah,
sure. We can download it.
Yep, we'll do.
That's fantastic. Good work.
Now, have we got Duncan back? No, we don't. And I think that's it for Australia. And perhaps we'll go back over to the US now. And is Rich there? Or if Rich is not there, Ted, perhaps you'd like to introduce your folks. And we'll pick up Duncan if he pops back in.
Very good. We'll start walking through them, or you can. We'll start with me. I'm trying to play with some hardware, but running into some RFI just to show you fun pictures. There are three antennas at least, pointing up at the sky along a fence, and I'm trying adding interferometer, which is really just an antenna array, and seeing what I can do with it. Each one of the antennas has an LNA attached right to it. The way I'm combining it, just so I can pass power to the LNAs conveniently, is with a so-called combiner, which is just shorting out the shields of the cables, as well as the connecting together, and then the centers of those coax connectors together. So that's called combining, just shorting them together, and see what I get. But so far, this location, right next to a school and a cell tower, seems to show a whole lot of radio frequency interference. And so that's what I'm fighting now. I moved one antenna behind the building and suddenly got really quiet. So we'll see what happens.
You do know how many phones are going off in that school, Ted?
Oh, I know that. At least behind the building, even if it does face the parking lot of the high school, that's not too bad and has worked before.
Oh.
We'll see, but apparently if I'm in view of the cell tower, That's probably a bad idea.
That's gonna eat you alive, yeah.
Yeah, so this is what I'm proving. That's the news from here. Let's see who we got. Bob is next on my little list. Bob, you want to talk to us?
Okay, I'll do that. I'm gonna share my screen here if it'll, yeah, share. This is some of my data on the monitoring the 10 megahertz, 10 megahertz signal. And this, I selected this because this was around the 15th of October, and I know there was a lot of sun activity, and you can see how the 10 megahertz signal from WWB at my location was jumping around on that day because of the solar bursts that were happening. And so I've got two orthogonal antennas, and I'm sort of like collecting data, and I have been collecting data for a year, but I haven't done a lot of analysis of the data, and I need to do that. So if I have overlaid my other orthogonal antenna, and usually you don't see any or very little variation, but if I do it empirically with actual data, I probably can see some variation. And I'm also collecting magnetic data at the same time. So I've got that as well. And I spent a lot of time writing a piece of software to plot that data in 3 axes. I've got a magnetic 3-axis sensor buried 4 feet below the ground, and it stays at roughly 25 degrees C pretty consistently. And it's pretty accurate. It reads down in the a few nanotesla range, maybe down to 10 nanotesla. So it's really looking at the magnetic field differentially, but it's resolving some variations. And when we have those solar bursts, you can really see a lot of variation. And then I have meteor cameras here watching meteors, and lately I've spent a lot of time on a computer that's been giving me trouble that I've got 4 cameras feeding in there, and it's essentially making a video of the sky all night long. It's part of the global meteor network. They supply all the software. Analyze the software with artificial intelligence software to separate the meteors from the airplanes and bugs and stuff. And I've had trouble, I think, probably because it's been kind of hot here in North Texas, and my hard drive in the computer was biting the dust. So I may experiment with a solid state drive, although I was convinced earlier that the rotating memory would be more reliable. But maybe that's a questionable thing, I don't know. And I've also got a muon detector or a cosmic watch. I've got 3 of them, and I want to record the information off of those things the way they were originally designed and set up by a fellow from MIT by the name of Spencer Axis. He set them up to just have a little display on them, or you could put a SD card in them and record the data. But I want to just have the data coming into one of my computer servers on my network and try to correlate that data with 3 of them stacked, spaced out a little bit, so I can get some idea of direction of the incidence of the muons, and hoping to, when one of these supernovas pops, to be able to detect that in the data. But those are my projects, and I'm working on as I have time here. And I'll turn it back to you, Ted, and let you go to whoever's next. If there's any questions, I guess.
Yeah, I've got a comment, question. Bob, yeah, great. The muon's quite interesting because you might see some effects, say, from magnetic or geomagnetic storms, so the forebush decrease, for example, or if you're lucky, you might even see a ground level enhancement. I don't think we've had one yet this solar cycle from the sun. So, yeah, there's some folks here I work with operate muon detectors in Antarctica and down here in Tasmania. And there's data on the internet, of course, that you can go and have a look at. You can find muon telescope measurements. I also do the WWV, WWVH Doppler measurements, and yeah, some good stuff there. And encourage you to keep that going, particularly if there's a strong gamma ray burst in the future would be interesting. I don't think anybody's seen the ionospheric effects of that using Doppler yet, but that would be interesting to look at.
Yeah, I should also mention that I'm only looking at 10 megahertz, but the group is trying to expand that and look at multiple stations using a receiver that's much more broadband. And Bill Karn, K9Q, has written some software that allow you to like monitor almost 100 megahertz with a decent computer. And using convolution, he can pick out the signals at different frequencies. And so you could, with his system, you can watch all the different time stations simultaneously if your antenna is capable of covering the bandwidth that you need. So
Bob, tell us that call sign again.
the guy that wrote the software is KA9Q, and his name is Phil Karn. He's a very, very sharp guy. I've known him for 30 or 40 years. And he used to do work with Qualcomm and data encryption and transmission for cell phone type stuff at one time.
Yeah, most of the commercial transmitters now, while they're not being controlled by atomic clocks, they're GPS locked, and they're usually pretty stable over short term anyway. So yeah, a lot of the commercial stations you can use as a short term frequency reference, and particularly the digital radio monodial stations. There aren't many of those, but they also have quite a stable carrier, and you can do some other interesting things with those. There's some free software to actually do some ionospheric studies with those.
Yeah, I'm using a Leo Bogner GPS locked frequency reference for my stuff, and
Yep.
several of the guys are, and even spotted some variation that WWV had in their transmissions and issues, and they're constantly working to knock those out, but they have them occasionally, just like anybody would, I guess.
Yeah, great. Thanks.
Thank you, Bob, for the update. Before I go to Tom, here's a warning, and then I'm going to go to Don first. Don, tell us all about your working hardware.
Oh, I think I've already rather impolitely intruded on Australian time with my enthusiasm for these little dishes. They're actually not so little, and I think it's a thing that's going to not last too long, and it should be taken advantage of. Why should you be cooking beans with something that could be actively looking at it? The only thing I might add to that is that the receiving hardware for the scope in a box that Sarah has should work very well with those antennas, I think, rather than the gridded antennas that they've been using. And the cost is actually less. I think we ought to be jumping on it, frankly, for the amateurs, at least here. I don't know if they're going to be available in Australia or not. I think shipping costs here are actually about $30, so it costs you about $100 to play, but it's a 1.5 meter dish. It's steel, and it's quite well made, I think. I think it's a fantastic buy, for at least for us. So,
Don, it sounds like you're going to have 50 of these things.
well, I'd like to have
Barbecue with
about
Don's.
I'd like to have about 4 of them so I could use the thing I've got that has 4 receivers in it. But that's maybe for another day. Anyhow, I have nothing to impart today except enthusiasm.
Very good. Tom, you blinked on and off. Come on back and tell us what's going on. We're calling for Tom, BFQ. Well, now we're calling for Rich. Rich, are you out there? Oh, or Tom's coming back.
Yeah, I really have nothing to report. I've just been listening and trying to see keep abreast of what people are doing, and nothing else really to say. And I don't know why it did not allow me to use the space bar to unmute me, but there it is. I had to click on the microphone.
We appreciate the extra effort. Sounds good.
And I'll turn
Hey,
it back to you.
thank you, Tom. Hey, Captain Wendy, you there? What's going on with your world?
Arr, let's see. Now that it's cooled off and I don't feel like my brains are cooking, I'm still trying to get myself together to move, which is like I have such ambivalence. On the one hand, I need to get rid of stuff. On the other hand, I'm thinking perhaps I should buy things before I move off into the middle of nowhere. And now that I've talked to Don, I'm thinking I have to get one of those things. If I move to a place where there's no power, at least I can cook dinner on the dish. And that's about it. That's about it for me. I hope that you give us fair warning before you cut us off so that I can save the chat. I've already saved it twice, and that's all.
Excellent, excellent. We're going to call on Rich in a moment. Preston, what's going on in your world?
Well, I really have nothing basically to report on. I've been doing a lot of reading. And I did go through, Professor Lockhart, was that his name? Anyway.
It's either Felix or Jay, depending on what
Okay. But anyway,
from the Green Bank Observatory.
Yeah, I got I got the great course that he made, and I think it gives a real good overview. So which is good to have every now and then, so you don't get lost in the fine points and lose sight of the overall view. So I enjoyed his teaching a lot. That's about it.
Very good. Last call for Rich. Rich, are you out there? You're busy, I understand. Did I get everyone who's not Australian? I think we have it all, Andrew. That's the news from our side. Thanks for all the news from your side. It's exciting, particularly the big dish assembled now. Hurrah. Well done, Steve.
Yeah, thanks, Ted. Yeah, it's great to see the folks in the US too. And yeah, we'll catch up. We'll get Duncan back in next time. Be interesting to hear how he's going with his pulsar measurements. That's another exciting thing that's happening over this way. And I guess the other thing which Rich might have let us remind us about was to get working on a Drake's Lounge Australia logo that we can put into the Sarah shop and have some of our Australia US merchandise out there. So encourage you to come up with a design for that. I'm not sure if Rich has actually got something already, but encourage folks to get cracking with their pen and paper and draw something up. Well, thanks very much, folks. That's it for this month, and hope to see you all next month, and stay safe and well.
Okay.
Excellent job, Andrew. Thanks very much. All the best, folks.
Thanks, everybody.